Okay, we're going to talk about exponential functions today. Okay, right? That's where you have like an initial value times a base 2, and the variable is in the exponent. Here's f of x, where I have initial value 2 times my base of 2, and the variable is the exponent. This is very much like geometric sequences because they are exponential. From algebra 2, you had a sequence of numbers 2, 4, 8, 16, 32. It's basically, if you wanted to find like the 20th term in the sequence, or the nth term, the 20th term, we take the initial value 2 and times it by the common ratio to, let's say, the n minus 1. If we wanted the nth term, we'd multiply it by the ratio, and the exponent would be the n minus 1. Notice, for me to get this fourth term, I multiply it by 2 3 times. It's always, nothing happens, you have an initial term, so I multiply by 2 to get 4. So for the second term, we use the ratio 1 time. To get the third term, we use it 2 times. So notice it's n minus 1. If I want the 20th term, this would be a times the common ratio to the 19th. We get our common ratio, r, by just taking a term and dividing it by the previous term. Like a to the n divided by a to the n minus 1. The second term divided by the first term. The third divided by the second. 4 divided by 2. 8 divided by 4. It all gives you a common ratio of 2. Okay? And that's these are like exponential functions here. Okay? That's just a review. Alright, so some common knowledge I want you to have beforehand is basically how exponents work, and even with fractions. 1/3 of the first power is 1/3. And remember, like here's fraction a over b to the 0 power is 1. Anything to the 0 power is 1. Alright, 1/3 squared. 1/3 times 1/3 is 1/9. 1/3 cubed is 1/3 times 1/3 times 1/3. 1/27. Notice, as fractions, as you multiply fractions, the value is smaller, right? Look how big the denominator gets. Okay, so the bigger the denominator, the smaller the value. 1/3 of the 0 power, 1. Now, 1/3 of the negative 1 is 1 over 1/3, which is 3. If you dividing by this fractions divided by a fraction, the same as multiplying the reciprocal. So 1 times the reciprocal of this is 1 times 3 is 3. 1/3 to the negative 1/2 is the same thing as 1 over 1/3 to the positive 2. Notice how these negative exponents are positive in the denominator. Okay? So 1/3 squared is 1/9, so it's really 1 over 1/9, which is 9. So notice, fractions with negative exponents actually get bigger. Okay? Fractions with positive exponents get smaller. Fractions with negative exponents get bigger. Okay, all right. Exponential functions. Here's some rules. F of x equals a times b to the x. A is your initial value. A cannot be 0. Okay? 0 times anything is 0. All right? B is the base. Okay? B cannot be 0 also, but if b is going to be greater than 0, okay, but b can't be 1. Okay? So b, this is what you're kind of multiplying things by, like in a geometric sequence, this is your common ratio. B is greater than 0, so it can be a fraction, but it can't be 1. All right? And we'll look at 2 graphs later when it's a fraction and when it's greater than 1, okay? If we keep multiplying anything by 1, it just stays the same, all right? So A can't be 0, B is greater than 0, but it can't be 1. All right, here's f of x squared. This is not an exponential function. The variable is down here is the base. This is a power function where you can plug in 3 squared, 4 squared, okay? Here's g of x equals 2 to the x. This is an exponential function because the variable is the exponent, okay? That's what makes it an exponential function. Here's some examples out of your textbook, okay? F of x equals 3 to the x. This is the same thing where a, my initial value, basically, I don't see one here, so it's basically 1 times 3 to the x. A is 1 and your base is 3. 3 is the base. G of x equals 6 times x is negative 4. Again, not exponential. My x is not an exponent. That's a base, like, okay? So x is not an exponent. This is not an exponential function, okay? All right, example C. H of x equals negative 2 times 1.5 to the x. It's exponential. your initial value, A, is -2, and your base is 1/5, or 1.5. Here's one it'd be kind of important that you understand. Let me kind of zoom in a little bit here, okay? All right, I'm not sure if I'm going to get... Okay, so k of x equals 7 times 2 to the negative x. Yes, it's exponential, okay? Your exponent is the variable, but let's break this down. Notice what I do here. I take 7 times 2 to the -1 times x, okay? And I'll rewrite that as what? 7 times 2 to the -1, and I put that in parentheses to the x power, okay? You remember how we raise a power to a power, we multiply -1 to the x, -1 times x. When it's in parentheses like that, raising a power to a power gets me that. So I can break it down to -1 times x, and I can group it as my initial value a times 2 to the -1. What's 2 to the -1? That's the same thing as 1 over 2 to the positive 1, or 1/2. So this really, right here, is 7 times 1/2 to the x, okay? So my base is a fraction here. Greater than 0, less than, it's greater than 0, and it's not 1, okay? All right. E, q of x equals 5 times 6 to the pi. Not exponential. Pi is a constant, right? No variable there. Okay. Here's some more examples. Here's the function f of x equals 2 to the x. So we're going to plug in different values for x. So f of 4 would be 2 to the 4. 2 times 2 times 2 is 16. F of 0, that's we're plugging in 0 here. 2 to the 0 is 1. F of -3 means that's what we're plugging in for x. 2 to the -3rd, which is 1 over 2/3, which is 1/8, or 0.125. Here's some fraction knowledge. F of 1/2 is 2. Well, what am I plugging in for x? 1/2. Okay, that's the same thing as, remember, 1 goes within here, 2 goes out here. That's the square root of 2, 1.414. F to the -3/2 is 2 to the -3/2. Okay, that's 1 over 2 to the +3/2. 3 goes with the numerator, or 3 goes with 2 here, I'm sorry, under the radical, like 1 did here. The numerator goes with the number, and the denominator goes out on the root. So that's 1 over 2 cubed, and then you take the square root of 2 cubed in the denominator, okay? All right. Here's some of these things when we look at graphs. Here's, 2 to the first, 2 squared, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th, 2 times 2 times 2 is 32. And let's go the other way. 2 to the 0 power is 1. 2 to the -1. Okay, negative. Now notice that my base is greater than 1. So notice how as we multiply, things get bigger. 4, 8, 16, 32. All right, and then things are going to get smaller now. Now my base is 2. So now I'm going to have 2 to the -1 is 1 over 2 to the +1, or 1/2. 2 to the -2 is 1 over 2 to the +2, 1 over 2 squared, or 1/4. -3, 1 over 2 to the +3, 1/8, and so on. Notice, as we have negative exponents, I have fractions here, and it gets smaller, okay? 1/16, and so on, okay? So notice, here's my base is greater than 1. As my numbers get bigger for the exponents, we get bigger. As my numbers in the exponents get more negative, we get smaller, okay? So let's take a look here at, here's basically an exponential function 1, my a is 1, times 1/2 to the x. So my base is less than 1. This is kind of what a parent function looks like for an exponential function when your base is a fraction. It's positive, but less than 1, basically 1/2 to the x. So notice, like, remember we went over our values, 1/2, okay, notice fractions, the big thing here is fractions get big with negative exponents. Notice 1/2 to the -2 is 1/2 to the -2 is 1 over 1/2 squared. 1 over 1/4 is 4. 1/2 to the -1 is 1 over 1/2 is 2, and so on. So notice, here's the graph. Basically what a graph looks like when your base is a fraction, less than 1. Negative exponents make those fractions numerators, and this would be 1/2 to the negative 1 is basically 2. 1/2 to the negative 2 is 1 over 1/2 squared, or 4. And as exponents get more negative, fractions get bigger. As exponents get more positive, fractions get very small, as we saw earlier. Okay? 1/8, 1/16, and so on. Okay, so this is what the graph looks like generally, and you should be able to understand what we're doing here. Okay? And finally, this is the graph of 1 times 2 to the x, or basically 2 to the x. Our initial value is 1. Okay, we kind of went over those values here. Okay? Notice we get we went over all these values before. With 2 as our base, as the exponents gets bigger, as the exponents gets more negative, it gets smaller. Okay? So this is what a graph will look like for an exponential function that has a base greater than 1, okay? One thing that every exponential graph has in common is this point, 0, 1, 0, 1, okay? Because anything to the 0 power is 1, okay? And this is before we do any vertical shifts or anything on it, okay? So here's your basic exponential function with your base greater than 1. Here's when your type of shape of a graph is when your base is a fraction. Okay. When b is greater than 1, it's considered a growth factor because things are growing. When b is a fraction, it's a decay factor. Things are decaying and getting smaller. Okay. All right. If you have the textbook, I don't think 5th period class does. We're going to be looking at page 276, 275 is where this starts. And we're going to have basically, here's some definitions. 276 is the page here. And 277, these are some of the examples I went over. Okay? And real quick, as I move this, notice here is values for 2 exponential functions. But notice, this is kind of like the geometric sequencing. If I divide this term divided by this term, I'll get 3. This term divided by this term, I get 3. And I can figure out what the base is, or the common ratio. But I can figure out, here's my initial, here's the exponent, okay? And here I can figure out what the base is, what the growth or decay factor is, okay? 4/3 divided by 4/9, if you leave change flip, will be 3. Just like 36 divided by 12 is 3, 12 divided by 4 is 3. Very similar to what we talked about earlier, okay? So exponential functions tomorrow, everyone should have a very good idea. Have a good Monday.